Hello and welcome to my tutorial on viscosity. So viscosity of a fluid, it relates to its stickiness and its resistance to flow. Running liquids have low viscosity while golden syrup and engine oil have high viscosity and can be described as the resistance between adjacent layers in laminar flow. The higher the viscosity of the fluid, the slower it flows through the pipe. And the viscosities given in the table above are all measured at the same temperature. So whenever you measure viscosity, you always have to have it at the same temperature in order to keep it a fair experiment. That's pretty obvious. But the viscosity of the fluid changes with temperature, and most fluids decrease as the temperature increases. Their viscosity, I mean. The fluids generally flow faster if they are hotter. So viscous drag on objects while moving through fluids. When an object moves through a fluid, you can get friction between the surface and the object and the fluid. That's viscous drag. It's like having the friction between fluid elements move past each other. If you can't remember what fluid elements are, go back and look at my tutorial on flow lines, and you can calculate the force due to viscous drag on a spherical object moving through a fluid using Stokes' law. So if I have a round sphere like this and it has force F applied to it, and in another colour, viscous drag can be marked as V. So this is the sphere falling in liquid. You can use the formula F equals 6 pi nRV. Now that n is not actually an n, it is the coefficient of viscosity. I forget which Greek letter it is, but that's not important. It's the coefficient of viscosity, or in layman's terms, the viscosity of the fluid in newtons per s per m minus 2, or pascals. Pascals is the preferred way to remember it, as that particular base unit is difficult to remember. Where r is the radius, v is the speed of the object. So when you float on an object of water, the weight of the object is balanced by an opposing force from the water. So if you try to push the object under the water, it will spring back to the surface as soon as you let go. So fluid pressure is an outward force exerted on all surfaces the fluid is in contact with, including the surfaces of anything immersed in it. So it's caused by the rate of the fluid, which means it increases with the depth. So here's my fluid, and I'm going to put a block in it. Now we all know what happens, that the volume seems to suddenly increase, and the block, if it can float, floats. So the result is that the fluid pressure is higher at the bottom than the object than at the top. The difference in pressure results in a net upward force on the object, as shown in the diagram. This is called upthrust. So the size of the upthrust is equal to the weight of the fluid displaced by the object, which is also known as Archimedes' principle, and it's for all fluids. So coming back now to the Stokes' law idea, if I get a new page, so if we have a ball bearing that has a mass of 3.3 times 10 to the minus 5 kilograms, and R is equal to 1 millimeter, and it displaces 4.1 times 10 to the minus 5, yep, very, very small units of water when it's fully immersed. So it's allowed to fall through the water until it reaches its terminal velocity. So calculate the terminal velocity if the viscosity of the water is 1.1 times 10 to the minus 3 nsm minus 2, or PA for pascals. So if we know that 6 pi RV equals W, its weight, and the upthrust U. I'll just write that again. W minus U, weight minus upthrust, because it also comes from this equation. This is the equation for finding the terminal velocity of a free falling sphere, falling at a constant velocity, or its terminal velocity. So the viscous drag is increasing according to the Stokes law until U plus F equals W. So this is the upthrust plus the force is equal to the weight. That's when it's reached terminal velocity. So this is the resultant force. So we can work out the resultant force using the very long equation 6 pi nr, sorry, not r. So we have an r there, and long line like that. And V is W minus U all over 6 pi n r. So if V is 3.3 times 10 to the minus 5 times 9.81, which is the gravitational constant, 4.1 times 10 to the minus 5 newtons. So all over 6 pi times 1.1 times 10 to the minus 3 times 1.0 times 10 to the minus 3. Now in the actual book I've got here, they're using 9.8, so they've gone and rounded it to 14. If you do the calculation now, we should get it slightly lower than that, since I've used it to a higher degree of accuracy by putting 9.81 there, but it shouldn't really matter. The velocity is 14 ms minus 1, so that's how to find the velocity. Now you can measure the viscosity using Stokes' law by knowing that the upthrust plus the force equals the weight, and this is also known as the equilibrium equation. You can go 4/3 pi r cubed pf g, where pf is the fluid of density. So you have Stokes' law again, 6 pi n rv. So you have 4/3 pi r cubed ps. This is all one expression, so I just haven't got room. Where ps is the density, not to be confused with pf, the fluid of density. So yeah, the fluid of density. And this could also be expressed like this: gr squared all over 9 times the velocity. So that is how to do it. You find the viscosity. Well, never usually told to do this. You usually only have to use Stokes' law, but in case it ever comes up, I have derived it for you. So here's a question. A student drops a marble into a measuring cylinder full of water. The marble sinks slowly to the bottom. So we need to draw a diagram of the marble falling through the water and labeling the three forces that are acting upon it. And if the marble was falling at a constant speed, then what was the resultant force acting on it? For part C, use the following data to work out the speed the marble was falling at terminal velocity, where the radius is 5.0 times 10 to the minus 3 meters. Mass of the marble is 5 times 10 to the minus 5 kilograms. The mass of the water displaced is 2.1 times 10 to the minus 5 kilograms, where G is 9.81. Viscosity of the water is 0.0011 nsm minus 2, or pascals. So I'll give you a quick 5-second pause. Okay, hopefully you used Stokes' law for part C. I did forget to write that up. So, answers once they load. So this is the diagram: up thrust, viscous drag, and weight. For B, the resultant force is 0, where W equals mg, 5 times 10 to the minus 5 times 9.81 is equal to 4.9 times 10 to the minus 4 newtons. So now we're going on to the gnarly bit, finding the velocity. So if you follow it through correctly and determine that 9 times 10 to the minus 4 minus 2.1 times 10 to the minus 4 is 2.8 times 10 to the minus 4, then you should get the velocity to be, once you input Stokes' law at the bottom, V to be equal to 2.7 ms minus 1. If W equals mg, then 2.1 times. Oh, I'm terribly sorry, I seem to have done this the wrong way round. So that's how you get that. So knowing that the drag of the upthrust minus the weight of the marble, you will get 0 newtons, and then you can apply it to Stokes' law. I just seem to have misread it as I did it right to left. This is why you never do notes late at night. So I hope you found this tutorial useful. I'm terribly sorry for all the clumsiness. Hope you found it useful, and thank you for watching.